Since humanity first carried out explorations of Antarctica in the late 18th century by James Cook and his crew, the icy continent has given up much of its mysteries over the centuries. Antarctica is the fifth largest continent in the world, almost twice the size of Australia. 99% of its landmass is covered in ice, and it's home to about 70% of our planet's fresh water and 90% of our planet's freshwater ice. Antarctica is the coldest, driest, and windiest continent on Earth. It's a perfect place for ground exploration, and that's why 4,000 scientists are living there. And recently, they found strange anomalies within massive ice sheets of Antarctica. So what is it? And why are scientists worried? Scientists have continuously surveyed much of the Antarctic surface since the early 20th century and have kept track of all the continent's ice shelves and their movements. In one such ice shelf, known as the Brunt Ice Shelf, they've recently discovered that an iceberg twice the size of New York City is poised to break away. A recent NASA release says that a crack has been growing at a rate of about 2.5 miles or 4 kilometers per year since 2012. The crack started from the southern part of the Brunt Ice Shelf and is steadily moving northwards and can soon meet with another growing chasm called the Halloween Crack that was discovered in October 2016, growing eastward from the McDonald's ice rumples in the northern part of the ice shelf. Although the Antarctica's ice shelves are in constant motion, rising with the tides, splitting off icebergs at its edges and growing again as inland glaciers feed it. But this type of anomaly is not regular at all for the Brunt Ice Shelf, as there has been next to no activity within the ice shelf. The glacier in question is around 1,700 square kilometers, or about 656 square miles, making it the fifth largest iceberg in the world that's currently being tracked by the National Ice Center in Suitland, Maryland. This news has sparked various safety concerns for scientists in the area, especially ones in the British Antarctic Survey's Halley Station. What exactly is driving these massive cracks to form in Antarctica's ice shelves? And what would be the effect on the ice sheet itself if this crack led to a complete breakage? Let's look at a similar situation that occurred in the last few years. A similar giant crack was discovered in the Larsen C ice shelf in 2016. It was the fourth largest ice shelf in Antarctica at the time. Just imagine, it had an area of 17,100 square miles or 44,200 square kilometers, which is an area larger than the state of California. But this crack was about to break off an iceberg with the length of 68 miles or 110 kilometers, a width of more than 300 feet or 91 meters, and a depth of 1,600 feet or 500 meters. More mysteriously, by mid-2017, in less than a year, the rift had extended another over 20 miles or 32 kilometers to a point where only 2 miles or 3 kilometers of unbroken ice remained, and breaking was an absolute certainty. And in mid-July, the iceberg finally broke off from the Larsen C ice shelf, taking away almost 13% of the ice shelf with itself. And as of April 2020, scientists reported A68 has broken up into 3 pieces and is floating northwards towards open waters. When it broke, the iceberg was one of the largest ever, twice the size of Luxembourg, and weighed in at almost 1 million tons. What's driving these huge breakages in Antarctica? And is Antarctica safe for now? Scientists are still trying to figure out this anomaly. Smaller carvings of icebergs are regular occurrences all over the shores of the continent. These carvings are very much natural occurrences, as losing icebergs to the ocean is how these ice sheets maintain equilibrium, balancing the inputs and outputs from ice streams in and around them. However, such large carvings from major ice shelves are not consistent with the natural pattern at all. Such large carvings leave the parent ice shelves unstable and more susceptible to breakages. There can be various reasons for such phenomenon. One definite reason for such occurrences is the accelerated climate change due to the rise of greenhouse gases over the last few centuries. Since the Industrial Revolution, the concentration of carbon dioxide has been rising exponentially at a rate of about 0.17% per year. This change is primarily due to the combustion of fossil fuels, but also to large-scale tropical deforestation, which depletes the climate system's capacity for photosynthesis. Climate temperature changes depend on the variations in the amount of carbon dioxide in the atmosphere. Carbon dioxide controls temperature because the carbon dioxide molecules in the air absorb infrared radiation. The carbon dioxide and other gases in the atmosphere are virtually transparent to the visible radiation that delivers the sun's energy to the Earth. But the Earth in turn re-radiates much of the energy in the invisible infrared region of the spectrum. This radiation is easily absorbed by carbon dioxide. When the carbon dioxide concentration is sufficiently high, even its weaker absorption bands become effective and a greater amount of infrared radiation is absorbed. As it prevents its escape into space, the trapped radiation warms up the atmosphere. Antarctica has experienced air temperature increases of 3 degrees Celsius in the Antarctic Peninsula. It's 5 times the mean rate of global warming, as reported by the Intergovernmental Panel on Climate Change. Over the past 50 years, the west coast of the Antarctic Peninsula has been one of the most rapidly warming parts of the planet. This warming is not only restricted to land, but also can be noted in the ocean surrounding it. Upper ocean temperatures to the west of the Antarctic Peninsula have increased over 1 degree Celsius since 1955. Thus, ice shelves in western Antarctica are particularly susceptible to warming oceans, as relatively warmer water eats away at the ice shelves floating over the ocean. Since 1992, it's averaged a net loss of 65 million metric tons of ice a year. One of the defining characteristics of West Antarctica is that the majority of the ice sheet is grounded on a bed that lies below sea level. When the ice sheet is attached to a bed below sea level, ocean currents can deliver warm water to its grounding lines, the location where the ice sheet attaches to the bed. In some spots, the bed lies more than 1.5 miles below sea level. When these grounding lines start to retreat, ocean water can infiltrate between the ice and the bed and cause the ice sheet to float off its grounding line. Scientists recognized that this is the first step in a potential chain reaction. Ocean heat eats away at the ice, the grounding line retreats inland, and ice shelves lose mass. And when ice shelves lose mass, they lose the ability to hold back the flow of inland glaciers, meaning those glaciers can accelerate and thin out as a result of the acceleration. This thinning only leads to more grounding line retreat, more acceleration, and more thinning. In all this push and pull, sudden fractures can occur, leading to massive breakages of icebergs like the one currently taking place in the Brunt ice shelf. Once these icebergs break away from its parent mass, it becomes more exposed to warmer ocean currents and melts faster. And as more ice flows into the ocean every year, it leads to an eventual rise in global sea levels. This is the biggest fear among scientists with climate change. For example, the Amundsen Sea region of West Antarctica, which is the most vulnerable to the rise in ocean temperature, contains enough ice to raise global sea levels by 4 feet, 1.2 meters. The most recent UN Intergovernmental Panel on Climate Change report estimates that by 2100, sea levels will rise somewhere from just less than 1 foot to about 3 feet, or 26 to 98 centimeters. But the vast majority of these projections do not take into account the possibility of major ice loss in the form of massive breakages in Antarctica. The Amundsen Sea region is only a fraction of the whole West Antarctic ice sheet, which, if melted completely, would rise global sea levels by about 16 feet or 5 meters. This eventual sea level rise will have a profound impact on our civilization as we know it today. In the extreme scenario, if most of the Antarctic ice melts, the existing coastline of our present continents will be completely unrecognizable, raising the sea level by 216 feet or 66 meters. In North America, the entire Atlantic seaboard would vanish, along with Florida and the Gulf Coast. In California, San Francisco's hills would become a cluster of islands, and the Central Valley a giant bay. The Amazon Basin and the Paraguay River Basin in South America would become Atlantic inlets, wiping out Buenos Aires, coastal Uruguay, and most of Paraguay. Although Africa would lose less of its land to the ultimate sea level rise. However, in Egypt, Alexandria and Cairo will be swamped by the intruding Mediterranean. In the European continent, London would have been completely swallowed underwater. Venice will be reclaimed by the Adriatic Sea. Netherlands will have long since surrendered to the sea, and most of Denmark will be gone too. Meanwhile, the Mediterranean's expanding waters will also have swelled the Black and Caspian seas. Asia would be completely changed as well. Land now inhabited by 600 million Chinese would flood, as would all of Bangladesh and much of coastal India. But how to predict these sudden anomalies and whether these big calving will lead to a collapse of the ice shelf itself? At present, the anomaly under the Brunt ice shelf is still progressing, and both cracks are moving towards one another. This has allowed scientists to take some risks and monitor the process in great details. This research has already yielded a lot of new data and prediction models to further explain these anomalies under the ice sheets of Antarctica. That's all we have for you today, folks. Subscribe to our channel to keep getting videos exploring the latest scientific news around the globe. Also hit the notification bell so you're notified every time we release a video. Thanks for watching.